Okay, this is the first lesson video for our next unit in multivariable calculus. And this next unit, we're going to start talking about vectors and the geometry of space. And so this is where we're really going to transition from what we were doing in chapter 10, kind of getting the basics of parametrics and polar equations. And now we're going to transition into vectors, and especially three-dimensional vectors. So we're going to start getting into the whole idea of multivariable calculus by doing a little bit of work on three-dimensional systems. So to start with here, this video that I have for you today is going to be super short because this is not difficult stuff. More than anything, what you're going to get out of this lesson is what you do with your practice, where you practice graphing, you practice with the coordinates, really just getting that 3D perspective into your drawings and being able to view those three-dimensional images in the coordinate plane and being able to interpret where the points are and that kind of stuff. So what I've got here is just a graph of the three-dimensional coordinate system. This is sort of our standard graph. Now, sometimes I get the question about, does it matter if you switch the X and the Y axes when you do your three-dimensional graphs? And the answer is yes, it does. When we get into cross products in a couple of weeks, you will see that in order to have the Z-axis pointing up, I've got to have the correct orientation between the X and the Y-axis. And in addition to that, you just want to be thinking about the XY plane in the same way that we think about the XY plane when we're in 2 dimensions. So make sure you've got that same relationship between the X-axis and the Y-axis. So you can see over here to the right of this coordinate system, we've got 3 planes, the XZ plane, the YZ plane, and the XY plane. And those are just the planes that we would be operating in if we were to not have, for example, if we're in the YZ plane, that means our X is always going to be 0. Or if we're in the XY plane, that means our Z is always going to be 0. Or if we're in the XZ plane, that means our Y is always going to be 0. So sometimes we'll operate in those planes, but primarily we're going to operate within the three-dimensional coordinate system. In addition to that, you can classify where your points are located in the three-dimensional coordinate system by referring to what's called an octant. So in octants, if it relates to what we do in the 2D system. In the 2D system, we had quadrants because there were 4 regions of our graph. So if you think about it with a three-dimensional system, there are 8 regions where a point can be located, and sometimes we classify them by an octant number. Okay, so this is just an example of how we would plot points, and this is sort of the standard way that things are drawn. It is very helpful when you're plotting in a three-dimensional coordinate system to label 1 or more points, because a lot of times when you put points on a 2D paper or a 2D surface and you're trying to represent 3D, depending on what your perspective is as the viewer, you may view that point in one region versus another where it's intended to be. So if you label points, it makes it a lot easier to display what you're trying to display and for others to read what you're trying to display. Okay, so we have just information here about the 3 planes and then also the X-axis, the Y-axis, and the Z-axis. And again, that's all stuff that you kind of already know, but it's just something that we have to make really clear in our minds because we're going to start working in 3 dimensions almost exclusively moving forward. And so you've got to get your head wrapped around the idea of working in 3 dimensions. Now, when we are graphing, a lot of what you're going to do on this assignment is just going to be doing graphs. When you graph a plane, we typically display a plane just with a parallelogram. A plane is actually going to extend forever in the directions in the plane that it's in, I guess I should say, but in the directions like the X direction and the Y direction, if you look at this Z=3 plane. So in reality, it's not a parallelogram, it's extending into infinity where Z is equal to 3. Same thing with this graph where Y is equal to 5. It's extending, infinitely in the Z direction, infinitely in the X direction. So when you graph these things, it is helpful if you show the intersection point between your plane and your axis. And that way you've at least got something that's representing where that plane is located. And obviously, it's also helpful to have what the actual equation of the plane is so that you've got that for reference. This is an example of a cylinder. Sometimes with our cylinders, we're going to have a fixed height. sometimes we're going to describe surfaces that are cylinders, and we're going to have sort of infinite distances that are going to be associated with what we're calling the height. So when I have you graph these, I think I defined a height, but if I don't define a height, you're going to need to put one in just to make it clear that it is a cylinder. But if it needs to be an infinite cylinder, you can extend it out. However, it gets a little bit harder to indicate the shape when you're trying to make it look infinitely extending in both directions. Okay, so just for some notation, so a lot of times when you're dealing in a 2D or a XY coordinate plane or a two-dimensional coordinate system, we'll see that we're in the two-dimensional real number system. And this notation that you see here, you've probably seen R2 before, and maybe you've seen R3 a little bit. But when we're dealing in 3 dimensions, we're going to refer to it as R3. So that tells me I'm working in a 3-dimensional coordinate plane. So we've got some really simple stuff that we're going to do here in this section. And one of the things that they're going to ask you to do is to find the distance between points. So distance between points in 2 dimensions, we're essentially using the Pythagorean theorem. And when we extend the distance into 3 dimensions, it's actually the same thing. It's the same setup. It's the same logic behind where our setup comes from, or our quote unquote formula for the distance formula comes from. It's all the same idea. So the only difference now is we have to take a third coordinate into account. So you can see this distance that you have here, the distance between some point P1 and some point P2, and we're calling P1 X1, Y1, Z1, and P2 X2, Y2, Z2. So we're just saying that the distance there is going to be the difference between the x's squared plus the difference between the y squared plus the difference between the z squared, and then take the square root. So again, same logic as before. When we found that distance before, we would find that the distance between 2 points was x2 minus x1 squared plus y2 minus y1 squared, and that would have been it in 2 dimensions. So now we're just taking that third coordinate into account. Okay, so really quickly here, when they ask you to find the distance between points 2, 3, -1, and 4, -1, 3, what I want you to do is just go ahead and pause the video and find that distance for yourself. It should be quick and easy, and then you can come back and you can check your answer on that one. Okay, so here's what you should have found for the distance between the points. You can see my change in x's, change in y's, and change in z's. The main thing is you just want to make sure you go in the same order. It doesn't matter which one you call point 1 and point 2. You just have to use the same order between, the x coordinates, the y coordinates, and the z coordinates, so that you're getting that consistent measurement of, 0.2 minus 0.1 or 0.1 minus 0.2, whichever way you do it. So in this case, the distance was 6. So not really anything difficult to do. One of the shapes that we are going to use a lot when we're dealing in 3 dimensions is a sphere. And this is one of the basic shapes that we use. You may have seen the equation of a sphere before, but even if you haven't, all you have to do is think about the equation of a circle in 2 dimensions. And similar to what we did with the distance formula, you can extend the equation of a circle to become the equation of a sphere just by adding in that z measurement. So when we're working in a circle, we have a center point HK. When we're working with a sphere, we have a center point HKL. And the L is just basically that z distance that we are away. So remember, when we talk about a sphere, we're just talking about a center point, and then if we go the same distance in any direction away from that center point, some radius distance, that's what's going to create the surface of that sphere. So when we have a sphere that's not centered at the origin, that's when we're going to use this form right here. And when we're centered at the origin, that standard form for, for the equation of a sphere is just going to collapse down into this. X squared plus y squared plus z squared is equal to r squared. Okay, so what I want you to do here is find the center and the radius of this sphere. So you'll notice that this is not given in the standard form. So what you're going to need to do is work through this, solve it out a little bit, group things together, complete the square, and get it into the standard form, and see if you can come up with where the center and the radius is. So pause the video, solve that out, and when you come back, we can talk about the solution. Okay, so here's what you should have come up with for that one. And you can see I showed my basic steps for this. So we had coefficients of 1 for the x, the y, and the z, so that made this pretty easy. But I'm just completing the square. And then I've got my x expression factored, my y expression factored, and my z expression factored. The common mistake that people make here is they forget to add what's on the left side also to the right side of the equation. But you can see here, we've got the equation in our standard form. And once we've got it in that form, this is my standard form, now it's really easy to see the center. So the center is at 1, 2, -4, and the radius would be 2. Okay, so when you go through this assignment, the stuff in the book that you do, the questions out of the book, they're going to be fairly simple. The main thing to be remembering about this is you want to get your brain to where thinking in 3 dimensions is not a challenge. And it's probably, for some of you, not going to happen right away. Some people have the ability to think 3-dimensionally when they're working in math very, very quickly, and it's just kind of seamless. For some people, it's a little bit more of a struggle at first. So don't feel like if you're struggling at first that it's going to continue on forever. It just may take your brain a little bit longer to start to map things in that 3-dimensional space as opposed to the 2D plane that you've got a lot of practice with. Okay, so in addition to what's in the book, the other thing that I put together for you, this is at the end of the attached notes to the video. So I also attached some isometric dot paper into those notes. So what I want you to do, just for a little bit of graphing practice, is I want you to actually plot what's given here. So you've got some points, you've got some planes, you've got some cylinders, you've got some cones, and then you can see I've got some inequalities there as well. So again, the idea behind this is that I'm trying to get you to think 3-dimensionally, and by graphing them out on the paper, eventually what I want you to be able to do is know in your head what it's going to look like on the paper. So for some of you, like I said before, you may be able to do that now, but for those of you that can't, this is a good transition step into being able to visualize those things without having to graph them every time. Okay, so that's it for this video. We will get into 3-dimensional vectors in the very near future. So when we are working in 3 dimensions, this is going to be super important, even though it's very simple. So get started on that assignment. And next time in class, we'll talk a little bit about this, and we'll have a little bit of discussion about working in 3 dimensions.